Alright, so today we're at least starting our look at analytic functions. This is one chapter, but it might be too long for a single video. We'll see how it goes. But we're going to start with some notation. We're going to first off, we're going to let K be a field which is going to be complete with respect to a non-trivial absolute value. Because keep in mind that the trivial absolute value gives you the discrete topology, which every set is complete with respect to the discrete topology. And we're going to take the double bracket from x1 through xn be the formal power series. Of course, in n variables. We're going to use alpha and beta for n tuples with each alpha I, and likewise beta I, of course, going to be non-negative and an integer. Likewise R and S are for n tuples. For strictly positive real numbers, and x and y are also going to be n tuples whose components are from our base field. We're going to set r to the alpha to be the product of each component ri, which is a positive real number, to the power of alpha I, which is a non-negative exponent. Let me set up. Likewise, x to the alpha is going to be the product of the xi to the alpha I. Sorry, I. We're going to have capital X alpha, this is our indeterminate, as the product of the nth indeterminate, the ith indeterminate to the ith component of alpha. The size of alpha will be the sum of its components. Keep in mind, these are non-negative, so we're not going to have any sign issues or anything like that. The factorial of alpha is going to be the product of the factorial of its components. Alpha choose beta is going to be alpha factorial over beta factorial times alpha minus beta factorial. Now, we're going to define the absolute value of x, the size of x, to be less than or equal to r as the size of each xi being at most the size of its corresponding ri for all I in the range from 1 to n. And of course you can make these if you make one inequality strict, the other one will be strict too. With comparing r prime and an r and an alpha prime and alpha similar, which is just this partial order component wise. Now we're going to set P, I don't really like the notation, but if I change it, I'm not going to remember that I changed it. So P of R of X to be the set of Y in the disk of radius R around X. I mixed up X and R there. So the size of the distance between X and Y must be at most R. And they call this a polydisk because we can define a strict polydisk to be, it's the same as what you'd expect. The same general setup, but this inequality here is strict. And if we don't specify X, it is assumed to be 0. Obviously, likewise for our strict polydisk. Alright, time for some actual math now. We're going to let f be the sum of a to the alpha times an indeterminate x to the power of alpha, and r is above. Then first off, f is said to be convergent in our polydisk around R, radius R, if the sum of the A alpha times R to the alpha is less than infinity. F is likewise said to be convergent in the strict polydisk of radius R if it is convergent in the polydisks of all radius smaller, so we don't necessarily we don't need that it's convergent on the boundary here, but all of the interior essentially. And this comes with a, now we get our first lemma here. And we're going to let f and r be as above. We're going to keep our f and r. First off, if f converges in the polydisk of radius r, there exists m such that, a constant m such that for all alpha, a alpha times r to the alpha is at most m. So these sequences are bounded essentially. And likewise, our second part is if there exists an m, constant m, such that the previous equation, that is the a sub alpha in the absolute value times r to the alpha is at most m, holds for all alpha. F converges in the strict polydisk of radius r and uniformly in P of r prime for r prime less than r. Proof. For part 1, we're going to take m to be the sum of the A alpha size times r to the alpha, which is finite by part 1. This is by our definition of convergence that we gave, that is the sum. This sum has to be finite. It's a definition of convergence. And the proof for part 2. So we're going to take an r prime less than r, and then the sum of a sub alpha times r prime to the alpha is the sum of the size of a alpha times r alpha, and then rescaling by r prime alpha over r alpha, which is at most going to be m times the sum of r prime to the alpha over r to the alpha, which is going to be m times the product of 1 minus the r prime I over ri to the negative 1. So f converges uniformly in P on the poly disk of radius r prime. Things are happening upstairs too. So f converges in the strict polydisk of radius r. Alright, so definition, we're going to let f be the sum of a sub alpha times x to the alpha. Then the sequence f is said to be convergent. Not saying that it's convergent in a polydisk, just it's convergent in general. If it is convergent in P sub 0 of R for some positive R. Now here's a remark. Let f be the sum of a sub alpha times x to the alpha be convergent in P sub 0 and the strict polydisk of radius r. For any x in the strict polydisk of radius r, the series times the sum of the a sub alpha times the x to the alpha converges absolutely and uniformly, of course, in any P of r prime for r prime less than r. Its sum f(x) is a continuous function of x. Oh, this is supposed to be f tilde. This all motivates a lemma which states that if this sum is 0, then f is going to be 0. Proof? But no, we're going to do this inductively, of course. If, for a base case for n equals 1, we're going to do the contrapositive, I believe. Suppose f is non-zero. Then f of x is x to the n times the sum of c to the I times x to the I, where I goes from 0 to infinity, with c0 being non-zero, m being non-negative. Now, the series, the sum of c sub I xi, that looks like it's the variable. It's supposed to be the it's supposed to be, looks like the series is supposed to be the indeterminate, is convergent. The function this series defines is non-zero at 0, and hence non-zero in a neighborhood u of 0 by continuity. Now x to the m is non-zero in the non-zero elements in U. So f tilde does not vanish identically on U. In fact, if m is positive, the 0 of f tilde at 0 is isolated. Alright, so that's our base case. Now let's let n be above 1. We of course assume the lemma for n minus 1, and here we're not going to do the contrapositive this time. We're going to suppose that f tilde is 0. write f to a new line as the sum over I of c of I from x1 to xn minus 1 times x to the I of xn to the I, for of course ci being in the polynomial, the power ring, something like that. The determinants from 1 to xn minus 1, of course. Since f is convergent in the strict polydisk of radius r, the ci are convergent in the n-1 dimensional polydisk with radius s, where s is r1 through rn minus 1. Now, by hypothesis, for y being y1 through yn minus 1, in the strict polydisk of, I keep calling it radius, I don't know if that's the right term, that's what I'm going to use, of s, the function g defined by g of xn being the sum over I of our ci tilde of y1 through yn minus 1 times xn to the I. This is going to be identically 0. Hence, by the case n equals 1, by induction, all ci tilde of y1 through yn minus 1 are going to be 0. Now, since as this holds for all y in P0 of S, all Ci are 0 by induction, hence f is 0. Okay. Sorry, one second. I'm trying to plan out exactly where we're going to end things off. Maybe a theorem there. So, anyways, sorry about that. By this lemma, thus, well, we may associate, I guess identify is the more technical term, a convergent power series f with its associated function f tilde. So now we're going to actually study our analytic functions here. Now that we've set up our context here. Definition. We're going to let U be an open subset of the n-dimensional vector space over K. And we're going to pick a function, we find a function phi from this U to K. Then phi is said to be analytic in U if for each x in U there is a formal power series f and a radius r, being positive, strictly positive of course, such that, well, first off, we have a strict polydisk of radius r on each x, which is all in U, because keep in mind U is open. And secondly, f converges in the polydisk of radius r, and for h in this strict polydisk of r, phi is just a translated version of f. So essentially we can find a power series converging with a positive radius at every point in our domain for this open range. And of course, if phi is analytic in U and x is in U, the power series f from x as above, as set out above, is unique and called the local expansion of phi at x. If you've ever taken a calculus course, a formal higher level one, this should all be pretty clear as analogs to the typical real case. So, theorem. I'm going to let f sum of a alpha, x to the alpha, where x is an indeterminate. This is going to be convergent in the strict polydisk of radius r for r positive. Then f is an analytic function in the strict polydisk of radius r. Like the proof, let x be in the open polydisk of R. We can then choose an R prime such that essentially R prime is between the size of X and R. And we can set S to be R minus R prime. Now note that X plus H to the alpha is the sum for beta at most alpha of alpha choose beta times X to the alpha minus beta times H beta, our typical binomial. So hence f of X plus H is going to be the sum over alpha of A alpha times the sum over beta less than or equal to alpha of alpha choose beta X to the alpha minus beta times H to the beta. Now to show that rearrangement of this sum is permissible, we will show first off summing over alpha, then summing over the beta being at most alpha of A sub alpha times alpha choose beta times X to the alpha minus beta times H to the beta is finite. So let the size of H be less than or equal to S. We're going to pick an S prime between the size of H and smaller than S. Then draw this term in the sum, this size of A sub alpha of alpha choose beta of X to the alpha minus beta H to the beta is at most A sub alpha times alpha choose beta times the size of X to the alpha minus beta times the size of H to the beta. And we use that the norm of P is going to be at most P itself when P is a positive integer to estimate this factorial. Thus the sum for beta less than alpha of A sub alpha of alpha choose beta of X to the alpha minus beta H to the beta is going to be at most the sum of beta less than or equal to alpha, and we can split this the size of our A alpha times alpha choose beta times R prime to the alpha minus beta S prime to the beta, which is A sub alpha normed times R plus S, R prime plus S prime to the alpha. Hence we have an upper estimate, and that's an upper estimate of this term here we need to show is finite, and our estimate is the sum over L alpha of the norm of A sub alpha times R prime plus S prime to the alpha, which we know is going to be finite. Okay. Now this sum is finite since f converges in the strict polydisk of radius r and the sum of r prime and s prime is less than r radius r. And this essentially gives us a lemma, I think for free. Mostly for free. We're going to let f be the sum of a alpha x to the alpha convergent in the strict polydisk of radius r, and we're going to define delta to the beta of f to be the sum for alpha being at least beta of r a alpha times alpha choose beta times our indeterminate x to the alpha minus beta. And then we have a few properties about this. First off, delta to the beta of f is convergent in the open polydisk of radius r. Number 2, for x in the open polydisk of radius r, then the series over summing over beta, delta to the beta of f to the x times h to the b, h to the beta converges in P, not the open polydisk of radius r minus the size of x. And third, once again, for x in P naught of r and h in P naught of r minus the size of x, f of x plus h to be the sum over the beta of delta to the beta f of x h to the beta. Now the first two follow from our estimate of the sum here. They follow from our sum itself, actually, was probably more clearly. For part 3 also follows from this proof, but it's maybe a little more nuanced to work out. We see that the sum over alpha of a sub alpha times the sum over beta smaller than alpha, if alpha choose beta, times x to the alpha minus beta times h to the beta is the sum over beta times the sum of alpha at most beta of a sub alpha alpha, choose beta, times x to the alpha minus beta, times h to the beta, which we know here is the sum over beta of our delta beta of fx times h to the beta, which is what we needed. Now the next step here is to generalize this construction to vector valued functions. However, we're actually not really at time, but I'm gonna call it here anyways because I feel like the next natural stopping point is gonna be like a long ways away. So yeah, a couple shorter videos today. It's just a more relaxed day today, I guess. I don't know. Thanks for watching.